Thank you very much. I hope that my screen is sharing at the moment.
Yeah, sharing okay.
Brilliant. Okay. So yeah, I would like to tell you about the upcoming Paleoclimate Modelling Intercomparison project. So as with CMIP, with CMIP7, there's a variety of different community MIPs, and this is one of those community MIPs, in this case, looking at paleoclimate. So I guess first I ought to say a little bit about why you might want to look at paleoclimate. And so it should be obvious to most people that the climate has not been the same throughout the whole of Earth's history, and we know that there have been times when it was much warmer than present, and there have been times when it was much colder. This particular figure here I've taken here is the first figure that's in the technical summary of Working Group 1, showing as you go from 60 million years ago towards the present and then up into the future scenarios, you can see how both the CO2 levels have gone from, or they were sort of up around 1,000 parts per million, and then they've dropped down, gone into some bits that are colder than the present, and then as we move into different future trajectories, we return to some of those higher CO2 levels. Well, we already have returned to some of the higher CO2 levels. And what you can also see with the maps in these figures are some multi-model mean temperature anomaly patterns for all the different future projections, and then for two different past climate states. In this case, the mid-Pliocene, which is about 3 million years ago, and the early Eocene, which is about 55 million years ago. And if you've got eagle eyes, you can see that the mid-Pliocene, the land mass is about the same where the continents are. But as you move back further into geological time, then the land changes its location. PMIP as itself, so the Paleoclimate Modelling Intercomparison Project, is over 30 years old now. It's one of the oldest modelling intercomparison projects, and it started off being just atmosphere only models that were forced by reconstructions of sea surface temperature, and it brought together the sort of the data reconstruction side to work out what those sea surface temperatures would be. And then as we've moved forwards in time and our models have got more advanced, we've devised more sophisticated scenarios, as well as increased the focus to look at different times. I don't really expect you to understand all the acronyms on this particular slide. I'm just putting it up to remind myself more that we've progressed as we've gone forwards in time. We started off looking at the MH, so where are we? MH, so the mid-Holocene, which was 6,000 years ago, and the last glacial maximum 21,000 years ago, as a warmer than present climate and a colder than present climate. And then we've added these additional time periods as we've gone on. I've got highlights here. I was going to say successes. At least lots of activity has gone on around this paleoclimate work, and I thought I'd highlight some of the achievements of the previous phases. And so I guess one of the main reasons for looking at past climates is that, unlike future climates, we actually have some knowledge about what the temperatures and precipitations were back in the past. Now, we don't have that from direct instrumental data, and so we have to reconstruct it from something that relates to the climate or is dependent on the climate, and then infer what that tells us about the climate. So it's an indirect measure of the past climate. And in this particular very messy plot, and again, I think this is more an example of how this is being used rather than trying to convey the actual information that's being done here. So this is an example of the benchmarking that was in the third chapter of the last IPCC report, and in each of these dots here is one of the old phases of PMIP, and so this is then the CMIP 6 models, and we're looking at various different regions, so say North America and Western Europe here, and the temperature changes in particular months. So we've got the mean temperature of the coldest month and the mean temperature of the warmest month, and the annual precipitation. So some key climate variables, and these are the temperatures that the models are projecting as being changes. And in this case, the mid-Holocene, which was warmer, and in this case, the last glacial maximum when you had the bit large ice sheets covering large chunks of North America. And what's important about these is not that there's a spread in what the models project, but the reason I'm showing it is the coloured phase behind, which is the average from the reconstructions. And so in this case, these particular reconstructions in this figure are using pollen assemblages. So researchers, not me personally, have dug down into sediment cores, normally in lakes, and analysed and taken out all the bits of pollen, put them under a microscope, identified what the different species are, looked at the changing fraction of those species, and that can tell you something about the climate in which that ecosystem was living. And that allows us to say which models are doing well and which ones are doing not particularly well. And so that's an example of using the past, the simulations of the past and the data of the past to do benchmarking. The other example I was going to one of the other examples I was going to highlight was climate sensitivity. And so Paleoclimate was one of the 4 lines of evidence that the IPCC used to constrain it, or to create its constrained estimate of climate sensitivity. And to do that, you need reconstructed global temperatures, which we need to collect from a range of different reconstructions and then compile them into a global set, which itself is a scientific challenge, as well as models that have different climate sensitivities that have simulated for those same periods. And so this figure again comes from the IPCC last report, although in this case chapter 7. And what you're seeing here is we've got some observations for various different time points, so the historical, and then this is the last glacial maximum, and this is the warm Pliocene, so 3 million years ago, where the CO2 was about 400 parts per million. And then this is the early Eocene, that was the really high bit on the figure that I was showing. The scale is changing here on the vertical axis. But you have the observations, and then you have the simulations. Each of these are a different model with a different ECS, equilibrium climate sensitivity. And what you can see is that although the observations sort of can constrain some of these, for say this last glacial maximum, if you have a model with a very low climate sensitivity, then that falls outside the range of the observations, and a model with a very high climate sensitivity falls also outside the range of observations, but in the other direction. And the same with some of these other paleoclimates. And so we can use the fact that we have models and observations to constrain the climate sensitivity of this setup. And then finally, I want to just highlight the possibility of going beyond just saying whether a model is, or evaluating how good a model is, to more formally pulling the information coming from how good that model is into a constrained future projection. And here's an example just recently that was in by He et al., so the group at the Chinese Academy of Sciences, who were looking at monsoon changes and the causes, or the causes in past climates that would have altered the monsoon are different than in the future. But if you look at the underlying mechanisms, you can see that the thermodynamic mechanisms follow a straight line. This is just showing here. So there's a relationship in the thermodynamic mechanisms at work and a relationship in the changes in circulation. And so we can see those in the past climate models, but we don't actually have enough data to constrain what the range of those setups are yet. There's still work to be done there. And so that's what's happened with the previous phase of the Paleoclimate model Intercomparison from a science perspective. From a MIP perspective, it was an endorsed part of CMIP7, and 22 different models and sort of participated and posted data on the Earth System Grid Federation. every model, to be part of it, needed to do an entry card, which was either one of the mid-Holocene, so 6,000 years ago, or the last glacial maximum, 21,000 years ago, which are simulations that have persisted right the way through all phases of PMIP, so that we can track model development. And then there were 3 other endorsed experiments, which were looking at the mid-Pliocene, but then a bunch of other experiments sort of outside of the formal CMIP6 setup, but that we were working with and collecting data, and the early Eocene that I've mentioned before is one of those. So for CMIP7, the MIP side of things is clearly still the same. That process of endorsing simulations is not operating in the same setup. So there's an assessment fast track, which has some really key simulations that need to be done quickly, and then the MIPs are taking more control over precisely what the experiments are. And there is a PMIP opportunity in the data request saying what information we would like. Within the fast track, there is a paleoclimate related simulation, and so this experiment starts from the PI control and then instantly changes the forcing to that scene of 127,000 years ago. So that's in the last interglacial, so the last warm period before we went into large ice sheets. And what's interesting about that is we have evidence from proxies suggesting that there was very little sea ice in the summer. The change in orbit that's related here means that the Arctic saw a lot more insulation in summer, and on the fringes of winter less insulation. So this is something that is driven by changes in the seasonal cycle, that lack of sea ice, but we do at least have some evidence of it. And so this proxy data, the figure here shows a proxy data set with some open circles showing that there was evidence of no sea ice in that time, and obviously a warmer climate associated with that. So we're hoping that many groups do that fast track simulation, the abrupt. If that is clearly not going to reach equilibrium because it's only running for 100 years. If you were to run that simulation on for even longer, then you would reach what is known as the LIG 127K is the experiment name, but it is the climate of the last interglacial. And that itself was featured in AR6, and you can find it in the interactive atlas. The climate of the last interglacial was 1 to 1.5 degrees warmer than today, with an increased sea level. I believe more that we've reduced our estimates of quite what that sea level is, and that was with a CO2 level that is something around pre-industrial values. And so there's this last interglacial simulation is an extension of the fast track simulation. We also are maintaining the mid-Holocene and the last glacial maximum simulations. The Pliocene simulation is going to be around as well. There's a substantial update of a simulation of the past 2,000 years, where a lot of the forcings have been revised with the new information that's there. And then we're adding formally a Miocene and an Eocene. Both of these, this is about 15 million years ago. This is 50 million years ago. So the land sea masks are changing under those substantially, which does in the Eocene also lead to warming that different land sea mask. That has higher CO2 as well. And so I just want to highlight, as well as thinking about these simulations, we've got several other experiments that we're planning. And for example, there's a carbon cycle simulation, PMIP carbon, that hopefully we can find some tie-ins with C4MIP. There's a high resolution effort, and then tipping point. So Atlantic hosing experiments have been observed in the past, and so there's a suggestion to mirror one of those. And also we'd clearly we see these experiments as providing evidence of past changes, and would clearly like to collaborate with other groups where that would also be interested in the bits of the climate system that are changing there. So for example, the abrupt 127K has been designed with sea ice changes in mind. and the Arctic, and so hopefully we can join with sort of SIMIP and past ice sheets with ISIMIP. And so, yeah, I think I'll stop there and invite questions.
Okay, thanks, Chris. That's really interesting. Jaya's got a hand up, but I think that's from the previous round, Jaya. But there is a question from Gavin
that's
Schmidt,
from
actually.
the previous round.
Okay, there's a question from Gavin Schmidt in the chat. I'll read it out because it's pretty interesting.
Please do, yeah.
Many models in CMIP 6 fail to produce a reasonable LGM, but this is not ever written up, i.e. the absence of evidence is actually evidence. Can we have a better protocol for reporting on the PMIP results this time round?
The answer to that is yes. And we can. I guess I have not really thought about how to do it, but it was a big problem. For example, the analysis of the last glacial maximum runs was taken on by the French group at LSE using the IPSL model, and I still have not managed to get their model to perform that in their case due to some issues with sea ice and the model accidentally forming kilometers of sea ice. And yeah, we really should, and I guess that's probably something that we can use the sort of the Journal of Null Results and that kind of initiative that's come out to write up some of these experiments that are failed, because it's quite hard to write up something that just doesn't work. But yeah, I completely agree with that, Gavin.